R tutorial number 5, Descriptive and Inferential Statistics in R. In this tutorial, we will cover reading in data and setting the working directory, and we will primarily focus on descriptive and inferential statistics in R. So with descriptive statistics, we'll look at how to summarize data for interval ratio level variables, for nominal variables, and for ordinal variables. And inferential statistics will primarily focus on hypothesis testing. So we will review hypothesis testing for single sample means and proportions, for two sample means and proportions, and for ANOVA. So let's first start by downloading and saving the data in R code files. The files are located on the course website. The data file is named ab.survey.csv, and the R code file is named r.tutorial5.code.r. Once you have those saved in a specific directory, you want to set your working directory. And the working directory for this tutorial should be where you have saved the data and R code files on your computer. So let's do that now. We can do that by going to Session, Set Working Directory, and either choosing our directory manually or setting it to our source file location. So let's set it to our source file location. You can see that we've done that here. We've set our working directory to where this code file is saved. And once that's done, we can read our data file into R. If you are in the correct working directory and have used the same file name, the following code should read in your data and call it data. So here we use the read.csv function. We have the name of our data set, and we also want to say header equals true in order to use the first row as our variable names. So let's read that in now and see how that goes. All right, we've read in our data. We can see here in our workspace that it's now here. We can also look at the dimensions of our data using dim, the dim function. So here we can do that, and we see that our first entry is for our number of rows or cases. So we have 1,144 cases, and the second number is for our number of columns or variables. We have 15 variables. In addition, we can look at our variables by name and see that we have age, education, employed, and so on for our variables for our variable names. And in addition to that, we can also get a summary of all of our variables in our data sets using summary. So if we do that, we can see our variable names, but with also some basic summary statistics to go along with it here. So once you've gone through these basic data setup commands, you can then see if everything looks all right, if you're missing any variables, and you can also check the code book to see. If everything looks good, you can then attach your data set with the command attach. This command attaches the data set to your workspace and makes it easier to call your variables and perform different functions with your variables. So let's do that now. So now that we've reviewed our data and we have it attached, we want to start with some basic descriptive statistics. And here we want to calculate measures of central tendency and dispersion in the 2010 Alberta survey. Let's start by summarizing our data for our interval ratio variables. There are several functions that are helpful here. One of the first key functions is mean, which is basically called by using mean with the name of the variable you're interested in. So let's calculate the mean of age for our respondents. Type that in, and we can see that the mean age here is 49.99 years for our respondents in our survey. In addition to the mean, we can also calculate the median. So let's try the median for age. Here we see that the median age is pretty close to the mean at 50 years. In addition to these measures of central tendency, we can also calculate the standard deviation using SD. So let's calculate the standard deviation for age. We see that the standard deviation for age is about 15.73 years in this data set. We can also look at the range, and there are a couple ways that we can calculate the range. So one way we can go about doing it is by first calculating our minimum values with min and our maximum values with max. So let's do that for age. All right, we see that the minimum value for age is 18 years and the maximum value is 96 years. So to get the range for age, we could just subtract the two. So subtract the minimum age from the maximum age. And using that, we get a range of 78 years. Or we could also just use the function range, which will give us the minimum and the maximum values, and then we could subtract the two from each other. In addition to calculating the range, we may also want to calculate the interquartile range for the middle 50% of cases. In order to do that in R, you're going to use the function IQR in capital letters to get the interquartile range. So let's do that for age and see what we get. We use that function and we see that the interquartile range for age is 23 years. We can also do that in a little bit of a different way as well, using the function quantile. If we run that function for age, we see that we get the different quartiles this way. So we can see that at 50%, we get the median of 50 years, and then 25% is going to represent our first quartile, and 75% is going to represent our third one. So in order to get the interquartile range, we can then subtract them from each other. So we can do quantile age, 0.75 for our 75% one, minus quantile age, 0.25 for a 25% one. We do that, and we see that we have a difference of 23 years. The same result that we got for our interquartile range for age. So those are some of the basic functions that we can use to calculate descriptive statistics for interval ratio variables in R. For nominal and ordinal variables, we will generally summarize data using frequencies, proportions, and percentages. The two key functions that we're going to use in this case are table and prop.table. So to get the frequencies for a nominal or ordinal level variable, you can use the function table. So let's do that for our marital status variable. So we do table marital stat 1. We see the different frequencies across the different types of marital statuses. So 72 people were in common law relationships, 63 were divorced, 750 were married, 161 were never married, 28 were separated, and 70 were widowed in the 2010 Alberta survey. So that way we can get basic frequencies, but we may also want to see proportions and percentages. We can do that by adding on the function prop.table to our table. So if we do that for marital status, now instead of just the frequencies, we get the proportion of cases in each of these categories. So we can look across common law through widowed to see where many people lie in this particular variable. And we can also translate them into percentages by multiplying them by 100. So if we do that, we can now see that about 6.29% of cases were common law, 5.51% were divorced, the majority were married at 65.56%, 14.07% were never married, 2.45% were separated, and 6.12% were widowed. So this is an example of how we can look at some different frequencies and proportions for marital status in this case. Overall, when using descriptive statistics, we want to think about these different measures of central tendency and dispersion as well. Now that we've seen how to calculate descriptive statistics in R, let's move on to talk about inferential statistics. Inferential statistics allow us to use sample data to make inferences about a population. Let's first start with hypothesis testing for a single sample mean. So we have a question here about the difference between our sample mean and our population mean. According to the 2011 census of the Canadian population, the mean number of children per household is 1.1 children. We want to know if there's a significant difference between the number of children of households in Alberta, as we have from our data set, compared to all of Canada. So let's first go through our steps for hypothesis testing to calculate our obtained statistic by hand. We'll start with step 1, our assumptions. We're going to assume that we have a random sample and that we have interval ratio level of measurement since our variable is number of children per household. And we'll also assume a normal sampling distribution. In step 2, we'll state our null hypothesis, which is that our population mean mu is equal to 1.1. Our alternative hypothesis in this case would be that mu is not equal to 1.1. Then in step 3, we're going to decide on our critical region. In class, we would have used a z-distribution because it's a large sample, but R does not distinguish between the z and t distributions because when you have a large sample size, the two converge. So in this case, we'll use a t-distribution. We'll set our alpha equal to 0.05, and we'll do a two-tailed test because we're interested in whether or not the values are equal. In this case, our t-critical is going to be plus or minus 1.96 for 1,143 degrees of freedom. And notice here that our t is equal to what our z value would be if we were using a z distribution here. So we have plus or minus 1.96. In step number 4, we're going to compute the test statistic. Let's start by signifying our different variables that we'll need to compute our formulas. So let's start with x bar, which is going to be equal to the mean number of children in our Alberta survey. So we're going to say mean num.kids, which is our variable for number of children, and we're going to assign that to x bar. So here we see that the mean number of children is 0.645. We can also indicate our sample standard deviation S by getting the standard deviation for number of children. In this case, we see that's 1.07. We can also get n, the length of our number of kids variable, and our sample size here, which is 1,144. And finally, we can indicate our population mean mu, which we know from our question text. So now we have our values into R, which you can also see up here in your workspace. And once that's done, we want to use our formula to calculate our t obtained. So we can state our formula here in R, x bar minus mu, all divided by S, our standard deviation, divided by our square root of n minus 1. Let's do that and see what we get for t obtained. We do that, and we see that we get a t obtained of negative 14.43 in this case. So we use our formula that way, and we can also just simply plug our values into the formula that we have for our t obtained. If we do that, we get a value that's pretty close, but slightly different due to some rounding differences, so negative 14.37 in this case. In addition to just calculating our t obtained, we can also calculate the confidence interval for our estimates. So here we can use x bar and our formula for confidence intervals to get our lower range in this case, and our higher range in this case. So at the low end, we see it ranges from 0.58 up to 0.71. Overall, we see that our population mean falls outside of our confidence interval and that we have a t obtained that exceeds our t critical. So in step number 5, we can then make a decision and interpret our results. In this case, we want to reject the null hypothesis that our sample mean is equal to the population mean, because our t obtained of negative 14.3 is beyond our t critical of plus or minus 1.96. So instead of doing all this by hand, we can also calculate our t obtained using R, because R has a function that can do the work for us if we plug in the correct values, and that function is going to be t.test. So first, if we want, we can do help t.test to read a little bit about it. And here we see the t.test in the student's t-test, which performs 1 and 2 sample t-tests on vectors of data. So in this help file, we see the content of the specific function, along with the arguments that you're also going to include, some details, some values, and also some examples, which can be really helpful. So we have our t.test, and with that we want to enter our variable x, so num.kids in this case, our population mean mu, which was equal to 1.1, and also our chosen confidence level, which was 0.95 since we had an alpha of 0.05. And finally, we want to indicate whether we want a two-tailed, a two-sided test, or a one-sided test. So here we're going to say two-sided. So let's run that and see what we get. Well, we run that and we get a variety of results down here that you see. So here our results are going to give us our t obtained, our degrees of freedom, and also our p-value. So you can see that the t obtained here is the same one that we got by calculating t obtained by hand of negative 14.43 in this case. We see our degrees of freedom for n-1, and we also get this p-value. The p-value in this case will help us to make our decision. It gives us the probability of obtaining a test statistic at least as extreme as the one that was actually observed, assuming that our null hypothesis is true. And then we can compare our p-value to our alpha value. If it is less than alpha, we can reject our null hypothesis. So we see we have a very small p-value in this case, which is less than our alpha of 0.05. So here you will also see your alternative hypothesis, that the true mean is not equal to 1.1, and a 95% confidence interval and the mean of your variable in this case. So t.test gives us a lot of information. In addition to our two-tailed tests, we can also do one-tailed tests where we specify an alternative of less or greater. And you can see the results down here as well of what we're doing with a one-tailed test in R in addition to that two-tailed test. So overall, we can see that we can use R to calculate our test statistic pretty easily using the function t.test in the case of single samples when looking at means. In addition to calculating hypothesis tests for single sample means, we can also do that for single sample proportions as well using R. So here we have another example. According to the 2011 census of the Canadian population, 46.44% of adults were married at the time of the survey. We want to know if there's a significant difference between the proportion of married adults in Alberta compared to Canada. So let's start again using our 5 steps for hypothesis testing. Step number 1, we'll state our assumptions of random sampling. In this case, we have a nominal level of measurement because we're looking at the proportion of married adults, and we also assume a normal sampling distribution. Step 2, we'll state our null hypothesis, and our null hypothesis is that our population proportion, P sub mu, equals 0.4644. Our alternative hypothesis in this case would be P sub mu is not equal to 0.4644. Step number 3, we'll decide on our critical region. In this case, we're stating a z distribution, an alpha level of 0.05. We're looking at a two-tailed test, so that's going to give us a z critical of plus or minus 1.96. So now in step number 4, let's go on to compute our test statistic, and we'll first calculate it by hand in R. So in this case, we'll start by indicating our sample size n, which is equal to the length of our variable mer.stat1. And we can also then use our table function to determine our sample proportions. So we can do table mer.stat1, and we can see our different sample proportions here at the bottom of the screen. And in this case, we see that 750 respondents were married in the 2010 Alberta survey. So we can identify that as our sample proportion by taking 750 and dividing it by our sample size n. In that case, we see that our sample proportion is 0.65556. And in this case, we also want to indicate our population proportion of 0.4644. So we have all of that in there, and now we can use our formula for our z obtained for proportions that you see here to calculate our z obtained. Once we do that, we get a z obtained of 12.97 for this specific example. And in addition to using our formula, we could also just plug in our values and do that by hand. And we should get a very similar z obtained, which we do here in this situation. And in addition to calculating our test statistic, we can again calculate confidence intervals for our estimates using our formulas that we know for calculating confidence intervals with population proportions. So we can see our confidence interval at our lower end and at our higher end, and that we can see that we have an interval of 0.63 up into 0.68 in this situation. Now that we've calculated our test statistics and our confidence intervals, we can move on to step number 5 and make a decision and interpret our results. And in this case, we're going to reject the null hypothesis that our sample proportion is equal to the population proportion. In this particular situation, our z obtained is beyond our z critical. So that's how we would do it if we wanted to calculate things by hand in R, but R also has a function that can do the work for us if we plug in the correct values. And in this case, our function is going to be prop.test. So we can again use help to read a little bit about it over here. And what you see with our function prop.test, we're going to need to enter things again. So you want to start by entering the frequency of your variable x, which was 750 in this case, our sample size n, which was 1,144, our population proportion p, which was 0.4644, our confidence level, which was 0.95, and whether we want a one-tailed or a two-tailed test, we're going to use two-tailed and say that our alternative equals two-sided. So in this case, we get our different values here. We can see that in this case we have a p-value that is much less than our alpha level of 0.05. We can also see that our population proportion falls outside of our confidence interval as well. So this is how we could calculate population proportions and do a hypothesis test for a single population proportion in R. In addition to calculating hypothesis tests for single samples, we can also conduct hypothesis tests across two samples in R. Let's start with hypothesis testing for two sample means. So we have a question. We want to know whether the age of adults in Calgary is different than the age of adults in Edmonton. In our survey, we have data on both the respondent's location and age in our sample, so we can do this in R. So let's start by calculating things by hand and by going through our 5 steps for hypothesis testing. So in step 1, we'll state our assumptions. We have independent random sampling, an interval ratio level of measurement with our variable age, and a normal distribution. In step 2, we can indicate our null hypothesis that our two population means are equal. In step 3, we can indicate our critical region of Z or T distribution since R doesn't differentiate, an alpha of 0.05, a two-tailed test, and a Z or a T critical of plus or minus 1.96. In step number 4, we can then go along to compute the test statistic by hand. So to calculate different sample means and proportions for different locations in Alberta, you're first going to need to subset some of the variables for parts of the sample. So for example, if we want to know the mean age of respondents in Calgary, we use our function and variable age first for mean age, but we also want to include the category of location that we're interested in brackets. So location in this case is going to be equal to Metro Calgary. Two key things here, you're going to want to use a double equal sign for location, and you're also going to want to put Metro Calgary with quotation marks because we're dealing with words here. So let's try that and see what we get. We run that and we see that the mean age for people living in Metro Calgary is 50.46 years. Once we have that, we can then compare it to our other location Calgarys of Metro Edmonton and other Alberta. So here we see for Metro Edmonton, our age is about 1 year younger at 49.46 years. And since we're comparing Calgary and Edmonton, we can then use these for our X bars in our formula. So let's set X bar 1 equal to the mean age for people in Calgary and X bar 2 equal to the mean age for people in Edmonton. You can see down here that these equal what we've just seen beforehand. In addition to our X bars, we also want to get our standard deviations for age for each of these samples. And this works the same as getting the mean for age, except we're going to use the function SD. So let's get our S1 and S2 for Calgary and Edmonton. So we see our standard deviation for Calgary is 15.25. Our standard deviation for Edmonton is 16.27. We also want to get our individual sample sizes for each of these samples. So we're going to use length again, but we want to make sure that it's subset to our specific location for each of them. So we get our N1 and N2. We see that we have 382 respondents from Calgary and 379 from Edmonton. Now that we have all this information, we can plug it into our formulas. First, we need to calculate our standard deviation of the sampling distribution of our population mean for our formulas, however. So I've broken this down into 2 parts. And here we see we have 2 formulas for our sigma. And in this case, I wanted to show you how this works with using our formula for large samples, which we have up here for sigma.diff, and our formula for small samples, which we have down here for sigma.diff2. Let's run those. And what you'll see in this situation is that our results are very close because we have a large sample size. So with our formula for large samples, we came out with 1.1448. For small samples, we came out with 1.1445. So very close values. And we can then use each of these with our Z obtained formula to see what we get. So if we do that in both situations, we see that our Z obtains are also very close to each other at 0.87 for both of them. And in addition to doing that with our formulas with words, we can also calculate things for each variable by hand. So these are our formulas again down here, but I've put in each of the values to calculate them by hand. If we run all of that together, we see that again we get a Z that's very close, but not perfect because our answers differ slightly due to rounding. So that's how we would calculate things by hand in R, but we can also use formulas in R to calculate the difference between 2 means. We're going to use the same function as before with t.test, except we're going to enter each variable with our category. So here we're testing that the difference in means is 0, that there's no difference between the two. So here we're going to use t.test again, but now we have 2 entries. We have age for our location of Metro Calgary and age for our location of Metro Edmonton. We again have our confidence interval of 0.95 and our alternative of 2-sided for a two-tailed hypothesis test. So let's run that and see what happens. So here, again, we get our t-value, our p-value, our degrees of freedom, and our alternative hypothesis and confidence intervals related to a 0 difference at the mean. Here we see that we have a t-value close to what we had at 0.8761, our degrees of freedom, taking into consideration the sample sizes for both Metro Calgary and Metro Edmonton. And here we have a p-value that exceeds our alpha of 0.05. Due to this, we can move on to step 5, where we make a decision and interpret our results. And we see that our t obtained, like the one that we calculated by hand, falls outside of the critical region. We also see that our p-value exceeds our alpha of 0.05. We therefore fail to reject our null hypothesis that there is no difference in ages between Calgary and Edmonton. And this is a situation where we have a slightly larger sample size, so that small difference is going to equate to a significant difference between Calgary and Edmonton in terms of age. Alrighty, so we talked about hypothesis testing for 2 sample means. Let's talk about it now for 2 sample proportions. And our question here is, do marriage rates differ across cities in Alberta? Is the proportion of adults who are married in Calgary different than the proportion in Edmonton? So let's start by calculating things by hand in R and using our 5 steps to hypothesis testing. So step 1, we'll make our assumptions of independent random sampling, a nominal level of measurement, and a normal distribution. In step 2, we'll state our null hypothesis that our 2 population proportions are equal. In step 3, we'll decide upon our critical region and our distribution. So we have a z-distribution, an alpha of 0.05, a two-tailed test, and a z-critical of plus or minus 1.96. Now in step number 4, let's start by computing the test statistic by hand. So to calculate different sample proportions for different locations in Alberta, you're first going to need to subset some of the variables for parts of the sample. So for example, if we want to know the proportion of married respondents in Calgary, we would first use our function and variable mar.stat1, but we also want to include the category of the location that we are interested in brackets, just like we did with age when we were looking at means. So let's say we want the proportions for Calgary, or the frequencies for Calgary. We'll start with table, and this tells us the frequency across respondents from Metro Calgary. Let's say we want our proportions. We can also use prop.table again, and that will tell our proportions across Calgary. So these are the results for only people who listed their location as Calgary. We can also look at these results for people in Edmonton as well, using the same functions but changing our location from Metro Calgary to Metro Edmonton. So let's do that, and we see we have our frequencies and proportions for Edmonton as well. So let's combine what we just found here with our different formulas from the textbook. So we can indicate the frequencies for each of these from our tables. So we want to get F1, our frequency of married people in Metro Calgary. Here we're going to use table again and our location again, but we're also going to add this 3 in brackets at the end. The number 3 here means that we only want the third value in the table, the married people. So if we look down here at our table that we had for Metro Calgary, we see that our first value is for the common law people, the divorced people, and then our third one is for the married people. So that's why we have 3 here. So we do that for Metro Calgary. For F1, we get 250. As you see up here, there's 250 for married people. We can do that for Edmonton as well, which is going to give us 233. So you can see in this table over here that 203 people were married in Edmonton. We have proportions, or we have frequencies, but now we also want proportions from these tables. So we can do the same thing again with our prop.table for both of them and get PS1 and PS2. So PS1, the married people in Calgary, is 0.6545. PS2, the married people in Edmonton, is 0.6148. In addition, we want our sample sizes again, so our N1 and our N2, which we can use length, our variable, and our location. Let's get those. We have our different sample sizes for Calgary and Edmonton. And now that we have everything together, we can plug these things into our formulas for our textbook. So we have our formula for P sub mu, our formula for sigma with the differences between our proportions, and finally our formula for Z obtained. So let's run them all together and see what we get. Well, first we see that our P sub mu, our pooled one across our 2 samples, is 0.6347 for married people, We see that our sigma is 0.0349, and finally we get our z obtained for married at 1.1365 in this case. We could also just plug our specific numbers into the formulas to check in R. And we do that and we see that we have values that are pretty close to what we got with the others, but these do differ a bit due to rounding. So that's how we would do this if we were calculating things by hand. But again, we can use R to calculate a hypothesis test, again with our function prop.test. In this case, what we enter is going to be slightly different than what we did before. So first you want to start by entering the frequency of each of your variables, f1 and f2. We're going to put those together with the C in parentheses for our concatenate for our first overall value in prop.test. We also want to enter our sample size for each of the variables, n1 and n2, our chosen confidence level of 0.95 in this case, and whether we want a two-sided or a one-tailed test. So we can do that using what we have indicated for f1, f2, n1, and n2. See what we get for prop.test. And this is what we get for prop.test here. This is going to give us an x squared, which is our z obtained in this particular situation, our degrees of freedom, and our p-value for our sample estimates and proportions. In addition, we could have done this by just entering our specific values for our frequencies and our n's. And here you'll see that we get the same thing pretty much. So overall, we have everything together. We can move on to step number 5, where we make a decision and interpret our results. We see that our z obtained, like the one that we calculated by hand, falls outside of the critical region. Also, our p-value is greater than our alpha of 0.05. So therefore, we cannot reject our null hypothesis that there's no difference in marriage rates between Calgary and Edmonton. As a final topic in this tutorial, we're going to review ANOVA. So we're going to calculate the analysis of variance when we're conducting hypothesis tests with more than 2 categories in our independent variable. Our question here is, do the number of children in families differ based upon the marital status of parents? Let's use the condensed marital status variable for this problem. So we'll be using mar.stat2 in this problem. And first, let's start by looking at the mean number of children for each marital status. Remember that we need to subset this variable as well, and to get our 3 different means in this situation. So here you have your mean, and in this case your number of kids, which is going to be our dependent variable, and also our marital stat.2, which is our independent variable with our different categories. We can do this all at once to get our 3 different means. So we see that for never married people, the mean number of children was 0.2795. For formerly married people, the mean number was 0.1925. And then for married people, the mean number was 0.8054. So in this situation, it does look like we have a difference in sample means, but we want to know for sure, which means that we need to do a hypothesis test and go through our 5 steps. So we start with step 1, our assumptions. We have independent random samples. Our level of measurement is interval ratio for a number of children, our dependent variable. Our populations are normally distributed, and our population variances are equal. These are our assumptions for step 1. Now in step 2, we're going to state our null hypothesis, which says that the population means for number of children are the same across marital statuses. They do not differ for married, never married, and formerly married populations. Now in step number 3, we're going to indicate our critical region on our distribution. Here we're going to be using our F distribution because we're doing an ANOVA test. And we also have to decide on our F critical. For that, we need our degrees of freedom within and our degrees of freedom between. So we can calculate degrees of freedom with our n minus 3, our number of categories. So our degrees of freedom within here is going to be 1,141. We can also calculate them between using our number of categories minus 1, which here quickly calculated is 2. Now using Appendix D in our textbook, we can see that F critical for degrees of freedom equal to 1,141 and degrees of freedom between equal to 2 is 2.99. So we have our F distribution and our F critical score. Now in step number 4, we're going to calculate our test statistic. So because of the complicated calculations and our large sample size, we're going to let R take care of this one for us. However, I have included the code below if you're interested in doing the calculations by hand in R. So we can let R do the work for us by using the functions ANOVA and LM. ANOVA refers to the analysis of variance, and LM refers to a linear model. which is something we're going to discuss more later on with regression. So we set this up using ANOVA, but inside of that we're also going to say LM. And here we're going to set up with our specific variables that we have. So we have our number.kids, which is our dependent variable y. That's always going to be on the left-hand side. And we also have mer.stat2, which is our independent variable on the right. So let's do this and see what we get for ANOVA. All right, so we have a variety of things down here in this table from ANOVA. And this model is going to give us the degrees of freedom, df, the sum of squares, sum sq, the mean square, the mean sq, and our f value, the results of our f test, along with the probability of getting a value greater than f, which is the PR with our greater than f sign in parentheses. So the values in the row with our variable in it, mer.stat2, tell us the sum of squares, degrees of freedom, and mean square for between values. The values in the residual row tell us the sum of squares, degrees of freedom, and mean square within values. So these are the things we would be calculating normally. So we see we have our different values in our table here. We also have our f value. Now we can move on to step number 5 to decide and interpret our results. We see that our f obtained here is 35.287. That exceeds our f critical value of 2.99 by a lot. Our probability greater than f value also tells us that because it is below 0.05 by a ton in this case, that we can reject our null hypothesis that the number of kids does not vary by marital status. So this is how we would calculate ANOVA using the R function ANOVA and LM. We can also calculate ANOVA by hand in R. So if we go through, we can use our condensed marital status variable for this problem, which is what we've already done, and our different formulas for sum of squares total, sum of squares between, which I've broken up into 3 sets here, and also our sum of squares within. So if we run those things all together, which we can do nice and easily, we get our different values for sum of squares between, sum of squares total, and sum of squares within. Now we want to also calculate our degrees of freedom and our degrees of freedom within and between, which we have already done, but we can do again here. Now we want to calculate our mean square within, our mean square between. Do that. And finally, we want to calculate our f observed by dividing our mean square between over our mean square within. And here we get a value of 35.28676. Let's call back our ANOVA. And we see that our f values are very close to each other, as we just did here. So this is how we go through with inferential statistics and descriptive statistics in R. We've covered a lot of things today, so I suggest you go back through, maybe review some of it, and try some practice problems on your own as well.